This is 2025 AMC 12B problem 22. What is the greatest possible area of the triangle in the complex plane with vertices 2z, 1 plus iz, and 1 minus iz, where z satisfies absolute value 4z minus 2 is equal to 1? So this problem, we are using complex numbers. So we can write the vertices. So we can scale the triangle by a factor of 1 over z and just look at first at the triangle with factors 2, 1 plus I, and 1 minus I, and then worry about scaling it by a factor of z later, right? So first we look at this, we can draw the complex plane here. So we have 2, 1 plus I, and 1 minus I. So we think to ourselves, what is the area of this triangle? Well, this is 1, 1, 1. So base times height over 2, because this is 90 degrees. 2 times 1 over 2. So the area of the triangle is 1, right? Okay. Well, now we have to ask ourselves, what happens when we scale the triangle by z, right? Well, z as a complex number is going to, like, we can write z as r times e to the I theta, or rather, this is a bit of a complex way to write it, but rather just we can write it in polar coordinates as r semicolon theta. So basically z has some length to it, right? So if this is, say, this is our z here, z has some length to it, which represents the like scale factor. And then it also has this theta here, which represents a rotation around the origin. So when we're multiplying complex numbers together, the way multiplication by complex numbers works is you scale the like distance of the complex number by the distance of the other complex number, and you also rotate it by the argument of the complex number. So basically, what's going to happen to this triangle here is it's going to get scaled by a factor of the distance of z to the origin, right? Absolute value of z. It's going to get scaled, right, over to like here, right? This is where the triangle ends up, right? After being scaled, it's going to end up something like this. And then it's going to get rotated. The important thing to notice, though, is that rotating the triangle does not change its area. So, in fact, we don't care about the angle that z makes with the x-axis. We don't care about the theta value. All we care about is the r value. All we care about is absolute value of z. So, once again, just to reiterate, what's happening to the triangle is we're taking a triangle that has area 1, then we are scaling it by a factor of absolute value of z, right? So instead of the side lengths, right, these original two side lengths here were like root 2, this length was 2, right? Now they become absolute value of z times the square root of 2, absolute value of z times the square root of 2, and 2 times the absolute value of z. And so the area of the triangle, as you know, if you have like a scale factor k being multiplied by a 2D shape, then its area is going to be multiplied by k squared. So therefore, if the area of the original triangle is 1, it's going to end up being the absolute value of z squared. That's going to be the new area. And then we're going to rotate that triangle by an angle of theta, which is not going to change its area. So basically, at the end of the day, we have figured out that the area of the triangle in the complex plane with vertices 2z, 1 plus iz, and 1 minus iz is just going to be the argument of z squared. So now we can just worry about we're just trying to maximize absolute value of z squared given 4z minus 2 is equal to 1. Absolute value 4z minus 2 is equal to 1. So we still have a little bit of a challenge to deal with because we aren't really sure exactly what the structure of this is going to be. Well, if you're more familiar with these sorts of complex variable equations, you will know instantly that it's a circle. But the issue is this like linear term here makes it hard to determine where the circle is positioned or what way it's scaled. So a lot easier thing that we can do is just do a change of variables. So oftentimes when you're given a condition it's very helpful if you're given that like you're trying to maximize a value that is very simple, but the condition is a little bit more complicated. Like we have this linear term in z here. It's often going to help if we do like a change of variables to make this like inner value of our like condition. We're going to make the condition as simple as possible and then make maximizing the value we're trying to maximize, we can make that a little more complicated. Okay, so let's see what I'm talking about. So basically, we want 4z minus 2 to equal x. If we just had absolute value of x is equal to 1, then that should be very clear that that's just a circle, right? The set of all points in the complex plane that have a distance of 1 from the origin, that is the definition of a circle. The set of all points with a distance 1 from the origin, that is just going to be this circle here, right? So that's what x is going to look like. This is the graph of like what x looks like on the complex plane, all the possible values of x. It's going to be this circle. And then we can solve z. We get z is equal to x plus 2 divided by 4, right? When we move the 2 to this side, divided by 4. So now what we're trying to do here is maximize the distance of x plus 2 over 4 squared. And in particular, we don't really need to worry about the square part until the end, right? Because if we maximize this value, which is necessarily like a positive real number, its square is also going to be maximized as well. That's clear. Okay, so we're just trying to maximize the distance of x plus 2 over 4 from the origin, given that x has the distance of 1. So, of course, we could pull out some algebraic equations, let x be a plus bi, and just solve it via, bashing out the values of a and b. But instead, let's try to think about this problem geometrically. So remember, this distance, this circle of radius 1, centered at the origin, represents x. So this is our x circle. What will x plus 2 look like? Well, after we shift the circle 2 units over, this is what the x plus 2 circle is going to look like. Right? This is the set of all points that x plus 2 could be. And then we're going to scale it down by a factor of 4, which is going to be a little bit difficult to draw, but it's going to look just like that. So this circle here represents all the possible values x plus 2 over 4 could be. And we're trying to maximize the distance that x plus 2 over 4 is from the origin. So you can see visually here that if we have this circle here, that is still, of course, centered on the x-axis, right? All of the operations we did, adding 2, dividing by 4, those were like real number operations. So the center of the circle is still going to be on the real axis. So therefore, we can see that the furthest point distance from the origin is just going to be this point here on the far right end of the circle. So we can think about what that would have been originally, right? So this point on the x plus 2 circle would have been here. And on the very original circle, it would have been here, right? So x would have just been 1. So basically, x equals 1 is going to maximize the distance of x plus 2 over 4 from the origin. So if we do the math, 1 plus 2 over 4, that's 3/4. And now we just take 3/4 squared, and that's just going to give us 9 over 16. After you qualify for the AIME competition, be sure to check out our latest AIME preparation book of 5 practice tests to continue your Math Olympiad journey. And make sure to check out our full collection of AMC preparation books, MathTopia Press on Amazon. They include full practice tests and detailed solutions.